Okay, it's Atharv's lecture. Atharv, continue.
Hello,
You
people.
can do that. Yeah.
Okay, my pen isn't
Okay.
working very well today, so I could have some issues. Okay, let's just copy paste it 1 minute. Um, so the first thing is something you all may have seen. If you all have, then I don't mind if you'll tell it. It's a very basic idea. Show that for any n, there's some Fibonacci number that is divisible by n. Actually, if you have seen it, don't tell. You can try one of the buffer problems that the other people tried. These are the three buffer problems. Just take a screenshot.
Can you zoom in a bit? Like the quality is so bad, like I can't read the line text.
Hmm. Is this fine?
Yeah, this works. Yeah, I'm done.
Do you all have any ideas? Okay, so try to show that I'll write it down. And in case y'all don't know what the Fibonacci numbers are, they're defined by f1 is equal to 1, f2 is equal to 1, and for n greater than or equal to 1, f of n plus 2 is equal to f of n plus 1 plus f of n. Far as the buffers are over here. Did you get your screenshot? Okay. Wait, is this screen very laggy for y'all since it's laggy on my laptop?
No, no, it's fine.
Okay.
I think I have it, but I think I'll leave it to the others to try.
Okay.
Can we take it modulo M and then C by cyclicity? Because there should be a cycle, right? Infinitely many Fibonacci numbers.
Wait, why is there a cycle? Like, just because it's infinite, it doesn't mean it's a cycle modern. Like, it could be something like 1, 1, 2, 1, 1, 1, 2.
No,
It
because
just,
if we take the pair Fn and Fn plus 1,
yes.
mod
The key
M.
point is, yes, yes, that's correct. Okay, so did you all get what he's thinking, or should I? draw it out. Okay, I'll explain. This is weird. Okay, so the idea is we want to show that. So basically, Fibonacci numbers are defined on the previous two numbers. So it would be very nice if we have two pairs that are the same. So everything after is the same. So I'll formalize it a bit. So we have consider pairs Fn, comma Fn plus 1 mod n. Okay. Now the point is because there are finitely many possibilities for these, namely this is between 0 to n minus 1, and this is from 0 to n minus 1, so it's n squared possibilities. We get that there are finitely many possibilities for this. So by PHP, some two will be the same. Can someone who's not Ahan Pani show that, explain why this helps?
I mean, this essentially gives you that it's periodic model. Because, right?
Yes, it's eventually periodic. Because now we have f of r plus 2 is equivalent to f of s plus 2 mod n. And then we can easily show that from a simple induction that f of n plus r minus s is equivalent to f of n modulo capital N. Is this fine? Hello? Is anyone?
Yeah, this works.
But then how does this finish? Like, we've only shown that it's eventually periodic mod n.
Are you asking me or
No, I'm asking everyone. Okay, so I don't want to waste too much time on this problem. It's a pretty simple idea. So I'll tell you also, we know that f of r is equivalent to f of s, and f of r plus 1 is equivalent to f of s plus 1. But now the point is we can backtrack. So because of this, the
You
same way
can
we
go
forward
back for
track,
fn minus 1 and fn.
yes. So the way we backtracked, we forward tracked over here, we can go back over here. So we get f of r minus 1 is equivalent to f of s minus 1, so on till new page.
So if we have like 1 comma 1 mod m, we can backtrack it to 0 comma 1 mod m, and then fn minus 1 is divisible by m, right?
Yes,
Okay.
but we still aren't done yet because we need a term that's divisible by n. Like,
Yeah, so that is the one that is congruent to 0 because we're taking it in pairs, and since it cycles,
yes, it's
this
periodic. I agree.
infinitely
It's periodic. We know that f of 1, f of 2, on and on till f of t, and then this essentially repeats mod n. This repeats mod n. But this isn't enough. Why is this
there's
not enough?
at max only m squared pairs, so shouldn't we have by PHP at least one that is congruent to 0?
No. Because if we have a lot, then we know that some two have to be the same. Because think about what pigeonhole is. we have a bunch of pigeonholes and we are putting pigeons in them. It only says some two things are in the same box. There can be many, many empty boxes. So we can't quite say that there has to be something which is zero. Okay, so here's the magical idea. Notice that we can define an f of 0 to be 0, and this is completely consistent with Fibonacci numbers.
Yeah, so
It's 0,
that's what I
1,
said
1.
earlier. No,
It
I
is.
mentioned the idea of 1 comma 1 mod m, and then we go back and we trace it to 0 comma 1, and then f0
Oh,
is,
I must have
yeah,
missed that. Okay. So
that was
essentially, we
the
can
idea.
backtrack this, and then because there's 0, somewhere in our Fibonacci numbers apart from f0, which is not in our original definition, it's sort of like a phantom point in geometry. We can forward track it, and then we know that somewhere in our real sequence, we have an f of. So if this period is f of t, we get that f of t minus. So we have this period now, we get that f of t minus 1 is equivalent to 0 mod n. Is this clear to everyone? Apart from Nishant and Nahan Pani.
Yes.
Okay, I'm taking that as a yes. Can you explain proof of periodic? Okay, so I'll do it a bit on the side. So we have pairs f of k comma f of k plus 1, and we take these modulo n. I'm showing that it's periodic modulo n. Fibonacci numbers are not periodic. Periodic modulo n. And these pairs, there are only finitely many possibilities for them, right? So consider each possibility as a bucket. Okay. And you're putting these pairs into the buckets. Now, since there are infinitely many of these pairs and finitely many buckets, some two enter the same bucket. So say for some a greater than b, you have f of a, f of b, comma f of b plus 1 is equivalent to f of a, comma f of a plus 1 mod n. Okay. Now the point is from here we can get that f of b plus 2 is equivalent to f of a plus 2 mod n because of the definition of Fibonacci numbers. And then again, f of b plus 3 is equal to f of a plus 3 mod n. And because of this logic, this sequence is eventually periodic modulo n. Now what we do to show it's periodic everywhere, we can backtrack. So we know this one is equivalent to b mod. So we know this is true because of the definition of Fibonacci numbers. So from these two pairs, we get f of b minus 1 is equivalent to f of a minus 1 mod n. And then we just go back. Is that fine? Okay, nice. So, okay, and now do you get why this periodicness finishes? Or should I explain that once more? Okay, I'll take that as a yes. So, yeah, I'll move on to the next problem, which is of a very similar flavor, almost identical. So, even if you know the solution and you have seen it before, I don't mind you telling. So this is a previous ISL number theory.
It's just the same sort of thing.
Okay, could you elaborate a bit?
So, as in we define for up till, what do you call it? I mean, up till minus n plus 1, x minus n plus 1 to x minus 1, all of them to be 0. And then this is consistent.
Yes. Okay, so I'll just summarize what Bhairav said. It's basically the exact same problem. So our sequence looks something like 1, 1, no, 2, 4, 2 to the m minus 1. And then from there onwards, this term is the sum of the previous m minus 1 terms. No. It's yes, my bad. So this is the sum of the previous m terms, and then this is the sum of the m previous terms again, and so on. So we can do the same argument as Bhairav said. So we take blocks of m consecutive numbers. And take these modulo m. Like here we dealt with an arbitrary integer, which is capital N. Here our sequence is defined on m, and we're considering m. So it's pretty nice. And what we can do is we can get its periodic everywhere, the same way we did it over here. And now what we do is we introduce m minus 1 zeros before. And then that's basically it.
Actually,
So
shouldn't
then
it be something like, sorry,
yeah, what were we saying?
I mean, shouldn't it be something like m minus 2 zeros, then a 1, then all this?
Yeah, there should be 1 before this now, because then we'll have 1 plus 1 is 2, 2 plus 2 is 4, and so on.
Yes. So we have an m minus 1 once and 1 1.
Yeah,
So this 1 is the sum of these m terms, which is 1. This 2 is the sum of these, which becomes a 2, and so on. Is that fine?
yeah, makes sense.
Is this clear with everyone? Okay, I see 2 yeses. And I want everyone to be fine with this because like the stuff I do more, the stuff I build on from here is like very important. Okay, I'll move on. So I'll do a problem that appeared in the practice TSCs of this year's IMO selections. IMO TC practice TST2, I think. I enjoyed this problem a lot. I hope you all enjoy it too. Um, so this is the problem. It was proposed by Didul sir and Mainak sir. If you all have done it, then you can try out the buffer problems, which are these three. This one is on the same idea we've been discussing, but much harder. I'd like to finish this problem off fast so like we can move on to the next few ideas. Okay, so in this sequence, we have the same form of the recurrence, which we've been dealing with in the last two problems. And we can do the exact same thing we did. Wait, I think it's not mentioned in this state. I think I copy pasted the wrong statement of this. Okay, no, never mind. Yeah, so we have the same recurrence as before, and we want to show, so we know it's eventually periodic. Not eventually periodic, periodic everywhere. Modulo any n. So that's a good place to start with. Okay, so say x3 is less than or equal to 15. We want to show that somehow because of this periodicness, modulo n, these 2025 consecutive terms in this sequence, which are all primes, can't hold. So intuitively, we want to say that if, say, 10 is equal to x3, so 5 divides x3, we want to say that because of this periodicness, one of these 2025 consecutive terms is divisible by 5 by considering this periodic everywhere mod n, which is we're taking to be mod 5. So do you all see how to do this? Because it's not, because like the thing is, you want to show the period mod 5 is at most 2025 in this case when say x3 is 10. Do you all see how to do this?
Can you repeat what you said?
Okay, so you know how we're considering xn is periodic everywhere mod some n, right? So We are taking x3 to be less than 15. So say x3 is 10. So we have 5 divides x3, right? Now
Hmm.
what we want to do is something like if there are 2025 consecutive terms of the sequence which are all primes, we want to say that this is a contradiction because the sequence is periodic modulo 5.
Okay, got it.
Yeah. But the only way this would work is if the period modulo 5 is at most 2025. So I'm asking DLC why this is.
Wait, why did you consider x3 to equal 10?
No, this is just an example, so
Okay.
you sound better. So you'll see why the period is at most 2025.
Is it because because of four sorry, five places where the numbers can be if we write each of them modulo 5 like we did in the Fibonacci sequence, it is at max 4 to the 4, I believe here, and since that is less than equal or less than 2025, because if we have a 5 in any of those places, that modulo 5 is 0, and we have a number that is divisible by 5 when it's periodic. Is that
Yes,
somewhere
I think
there?
you have the right idea. So like remember here how I said there are n squared possibilities mod n, right? So the same way we got periodicness everywhere, here, since it's dependent on 3 terms, you'll need to consider triples xn plus 1, comma xn plus 2, modulo 5. And the key is there are at most 125 possibilities of this because it's 5 for this, 5 here, 5 there. So we have 125 possibilities. And because of that, in any 126 terms consecutive, some 2 will be the same. And remember over here, a period is the difference between the two things that are the same. So we got f of r and f of s are the same. So we got the period is s minus r. So here the period would be at most 126. And why does this finish? Because we have x3 and we have these 25 consecutive primes. Now x3 is 0 mod 5. Okay. So the period is 126. So we take these 126 hops of 126. And because 2025 is much bigger than 126, we eventually land here. So some prime we have here, p, it's divisible by 5. But it's clearly not possible because since x3 is 10, every number after that will be greater than 10 since a, b, c, d are positive integers.
Athar, I have a question just
Yeah.
regarding something you wrote down. X3 is greater than 16, so why have you written x3 is lesser than or equal to 15 if it's strictly greater than 16?
No, so we're saying for contradiction.
No, but what about the case of x3 is equal to 16? Isn't that also
Like
part of the bound?
less than or equal to 16, yes.
Yeah.
It doesn't make a big difference. So So now what's the maximum possible prime that can divide some number less than 16?
7, no, 11, 13,
13, yes.
13.
So say x3 is 13. Does the argument still work?
I mean, all that has to happen is 13 cube should be less than 2025, right?
Yes, but it's not,
It's not.
sadly. 13 cube is 2197. So
You can't have something modular 13 in one of the other spaces. So technically just 12 cubed, right? Because if we have a number which is their modular 13 in one of the boxes, here we have 3 boxes,
Yes.
then
precisely.
yeah.
So for our argument works perfectly fine. This argument we've been doing works perfectly fine for anything less than 13. But the moment we reach 13, we have to modify it a bit. So our modification is, so you know how we were taking these blocks? Okay. These blocks we had. These blocks were arbitrary. But now what we're doing is we're restricting these blocks within these primes. So you have some block here, some block here, some block here. And now because they're primed, we know something stronger. That these blocks can't be in one of 13 cube possibilities, they are in one of 12 cube possibilities. And this is less than 2025.
So we're done.
Yes. So then we do the same argument. So it's periodic here, it's periodic everywhere. And then because of that, we get something that's equivalent to x3 in our block, modulo the prime dividing x3, but that's a contradiction. Can you explain why it's periodic everywhere? Okay, so the point is, you got how it's eventually periodic now. So we can forward track over here. We have f of r plus 2 is f of s plus 2, and then we continuously go forward. So you have this block and this block, we go forward. And so on. Now what we do is, we can backtrack at the same time too. And get its periodic everywhere. Not just forward track. Is this fine with everyone? Oh wait, I forgot to make a frame. Let's make a frame. Yes, backtracking, not backbashing. Is everyone okay? Like no one is saying anything. Nice, okay. Okay, so this problem from the buffer, I'll put it in the preset also. This is like the hardest problem I've seen of this idea. It's a very good problem. It combines all of these ideas in smart ways. So I think you all should try it out. So I'll go to the next type of ideas. So this is a very, very nice thing. So I'll digress from a bit and I'll teach you some theory first. So what I'll talk about is PHP and CombiGeo. So the idea is, say you have a segment of length 1, and on this segment you have some more segments. And the length of these segments is at least, say, some number n. Show that there is some point which belongs to n of the intervals.
N is a natural number, right?
Yes, n is a natural number.
Can you repeat?
Okay, so I'll draw it a bit more colorfully. You have some segment of length 0 to 1. And in these segments, you have some subsegments of any length, such that the sum of the lengths is at least some n, where n is a natural number. Show that there is some point which belongs to at least n segments. Does this make sense? Like, it's intuitively true, but like, I want to see a formal proof for this. Does the problem statement make sense to everyone? Okay, so any ideas?
I think PHP might.
Yes, but how the class is PHP? You're basically telling me, oh, use PHP when the topic of the class is PHP.
Well, you can say that there have to be at least n segments, which maybe
Yes. But it doesn't quite say anything, right? Like, it can be a billion segments, all of them being very tiny. And then that doesn't quite say anything. Like, the point is that the sum of lengths is large, and somehow, because of this large sum of lengths, there have to be overlaps.
Can this be solved by probability too, using linearity of expectation? I don't have
Okay.
a proof written down yet, but I think that might lead to it, possibly.
Okay, tell your idea.
My idea was basically the average value of every single segment, right? And then drive a minimum by using the sum of the segments being obviously greater than or equal to n, and have that show that there has to be at least n seconds passing through one point or greater than n for some point.
Oh, if I get your idea, you're saying if someone asked for an explanation. So basically, we have in the segment 0 to 1 some segments such that the total sum of lengths of the segment is at least n, where n is a natural. Show that there is some point in at least n segments. But you're giving a very circular proof. Like you're saying that assume for the sake of contradiction, everything is in at most n minus 1 segments. But why does this imply that the sum of lengths is at most n minus 1? That is the question I'm trying to ask you. Yes, this is integration.
Yes, so I mean, technically, by linearity of integration, that
Yeah.
would just be direct, right?
Yeah, so the nicest way
That
to
was
say
my
this is
proof.
with integration. But I just wanted to introduce this idea to you to show that there's a continuous, like you can think of it as a continuous version of PHP. Like our previous thing was very discrete. Like you have 3 balls in 2 bins and you're done. But how do you define sum of length 3 and an interval of length 2 and show that there has to be an overlap? So I won't go into the formality of the integration, but I just wanted you to know I'll post some notes I wrote in the OMC server that could help you all. So I'll do a problem on this idea. Let me just put it. If for those of y'all familiar with linearity of expectation, could you all try to see why this is true with linearity of expectation? So we have a square of side length 1, and we have some disks inside it. Okay, side length 1. And the sum of circumferences is at least 10, is exactly 10. And now we want to show that there's some line we can draw which meets at least 4 of the disks inside our circles. Oh, you have a proof without integration. Could you speak up and tell?
It's in quotation marks without. So basically, just develop integration theory and just don't say integration.
Okay, and how do you propose to do that?
No, as in just define integration and then if you do that, it reduces to proving that the case n is equal to 1. It
But
will then
how?
be much easier.
But how? Like
So,
you're saying a proof without integration is to define integration.
yes, that
What?
is that that's what I meant. But then it just reduces to n is equal to 1. Yes.
Hmm.
As in define functions which are nice enough as in those are which are piecewise defined over intervals. Then define integrals of piecewise defined over define a function to be nice if it is defined piecewise over intervals on both 0, 1.
Oh,
Then then define integration on those functions, and then just to proof by that.
Yes. Okay. Like that's a bit overkill. Okay, so I won't cover the proof of integration. I'm gonna share some notes. Remind me if I forget on Discord. But basically, the proof of linearity of expectation is for each point, you consider the quote unquote random variable, which is equal to the number of points, number of segments, that pass through it, and the point is that this random variable we can show as expected value at least n. And because it has expected value at least n, since the sum of lengths is at least n, there's some point that passes through at least n, that at least n segments cover. And this is essentially the integration, because the only way we can say that the only way to say,
Wait, actually, can you repeat?
okay, so what I was saying is we have a point and we consider the quote unquote, the only way to actually formalize this all comes back down to integration. We consider the expected number of segments that pass through it. So in this case, it would be 3. This case, it would be 1, and so on. 2. Okay. And because of the sum of lengths is at least n, the point is we can say that the expected value of this random variable, quote unquote random variable, is at least n. And because it's at least n, there has to be some point which is on at least n segments.
Okay, right. That makes a lot of sense. Thank you.
Yeah. But now the only way we can actually formalize that the expected value is n is with integration. That y should be sum of lengths. Actually, no, you don't need integration for this proof. But like the reason it's at least n is linearity of expectation, because you can add up each interval's contribution. Is this clear to everyone? So does this proof make sense with linearity of expectation? As average value theorem? Yes, that's it, precisely it. But I don't want to talk too much about it, and that's not exactly PHP. Let's get back to the PHP part. So sum of circumferences is 10. Why is there some line that meets it at more than 4 points?
We can't really see the question because it's being covered by the pop-up.
Could you repeat?
We can't really see the question because it's being covered by the pop-up.
Oh, my bad.
Yeah.
Yes, that's precisely it. So what we do is we have a square, and a line in general can be too much. A line can be anything. So we take it very to be a very specific case when it's a vertical line. So you have a bunch of vertical lines, and essentially what we do is we take these circles and we consider just the diameter. Now the diameter is equal to the circumference divided by tau divided by 2 pi, which is so the sum of the diameters is 10 by 2 pi. So we have a bunch of horizontal diameters with sum of lengths 10 by 2 pi.
So it's
Another point
practically
is,
just the previous problem.
yes. And the point is this is at least 3. Method of moving lines, wow.
So 10 by 2 pi.
Diameter is circumference by pi, right? I'm dumb. Radius is circumference by 2 pi.
10
That's
by
what I was
2
wondering
pi
why 10 by 2 pi is at least 3.
should be greater than 4, right? For this to work.
Okay, no. I was a bit lenient over here. Here, in fact, greater than n minus 1 works.
Okay.
Because like think of it intuitively, like if the sum of lengths is at least 1, then there is some point that passes through 0 segments, which makes sense, right?
Yeah.
If sum of lengths is at least 1 minus 1, then we're given that some point is on one segment, which we know is true. If sum of
Okay.
lengths is at least minus 1, then some point is on 0 segments, which is it necessarily true? No. Or like n has to be a natural number anyways, yeah. Okay, is this clear? I'm gonna go on to because now I'm gonna do a harder problem on this idea. I hope this makes sense to you. Is this fine to everyone? Okay, Bhairav said yes. Anyone else? Okay, so I'll go ahead. Um, this is the problem. It looks like completely different, but it's on the same idea. He can be any integer, such that for all of the AIs and BIs and for all K and Z. So try seeing what this condition means. What does this condition mean exactly? Like it seems very random, but if you just try something until you figure out what it means. Can't we take C0 over K is equal to 0 and use... It says there exists some C, not for all C. And AI, BI can be anything.
We just have C always greater than mod of K, and then we're just directly done.
Wait, what?
C greater than mod of K, AI and BI are always positive. Since
No,
mod
K is not a fixed integer. It can be anything. So we have a C, and we have to show that for some C, no matter what K we pick, this quantity is greater than 0.
oh, okay, got it. Makes sense. Isn't the statement false then? Say we have some C, right? And K is a negative number that is greater than BI plus C. That
Okay.
means it's also greater than AI plus C. Oh yeah, that there is a contradiction. My bad.
Okay, so
Yeah, that is just
what does
greater
this
than 0.
condition
Yeah,
mean? If say we have A1 plus C plus K is times B1 plus C plus K is at least 0 for all integers K, what does this mean?
and both are either positive or both are negative.
Yes. So, well, for now, actually, that just ignore the C. We have AI plus K and BI plus K for all integers K, positive or negative, both positive or both negative. So say we take these numbers on the real line. By the condition we know AI is BI is less than AI. So say something like let me do a different color. BI is here and AI is here. What happens?
Use K is equal to 2 and then it's false.
Yes. K is equal to -2, not 2. K is equal to -2, not possible, as it violates this. So essentially, between any of these intervals BI and AI, if this is true, so in between B1 and A1, wait, why is my screen not working? Yeah. So between this B1 and A1, there is no integer. Is that clear to everyone? This true for all implies no integer in. Is this fine with everyone? This is the key of the problem, realizing this.
Wait, but can you show the problem statement again?
Yes. You read the problem statement carefully. It's very easy to misunderstand this one. So we have some BI and AI. such that b1 minus a1 plus b2 minus a2, so on till bn minus an, the sum is at most 1. And then we want to show that there is some c, exists a c, such that for all I 1 to n and all k in z, this inequality holds. So what I'm doing over here is I'm trying to understand what this inequality means.
Okay, so the original inequality given in the problem basically tells us that there is no integer between any AI and BI, right?
Yes, so we want to show that there is some c, exists some c, such that there's no integer between ai plus c comma bi plus c. Is this clear to you? Can you repeat? Okay. So what do you want me to repeat till? Until that is answered, do you all see why there is some c, so that all the translates, this is basically a translation of the interval, translation of ai comma bi doesn't contain any integers. How do you prove? Okay, let me repeat what I've done here. I'm assuming that is your doubt. So let denote x. So say we have that for some c, a1 plus c plus k, b1 plus c plus k is at least 0 for all k belonging to z. What does this mean? So I'm putting this as x and this is y. So we have x plus k okay, I won't use multiple colors, it's confusing me. X plus k times y plus k is at least 0 for all integers k. Oh yeah, so this was the problem. Inside the square of side length 1, you have many disks with sum of circumferences 10. There's some line that meets 4 of them. So we did some geometry on this. We took a line, we calculated its degree, and then we chased it, with projective transformations. Okay, so back to the problem. X plus k times y plus k is at least 0 for all integers k. Do you all get why this means there is no integer between x and y? Yes. Okay, nice. Is this clear with everyone?
Sorry, what did you say?
If this inequality, the one I'm pointing to in green, is true for all integers k, is it clear that there is no integer between x and y?
Yeah, yeah.
If and only if no integer between x and y. Okay, so we want to show that there's some c such that a1 comma b1 plus c no integers in between. Do you all see how to finish from here?
And I mean, what you can do is you can just look at a specific case, like the interval even, comma, even, and uh, okay, no, that one. So,
Okay, in this problem, let's change stuff up a bit. In this problem we did a while back, say the sum of lengths is at most um n. Okay, what can we say? Could you elaborate on that? What do you mean that some line has to coincide? Yes, there's a point in at most n-1 segments actually.
Let me just show the question once more.
Which
Uh,
question?
that one, yeah.
No, yeah, for strictly, okay, so if this is strictly less than, we can say at most n-1 segments. So in particular, if the sum of lengths is at most 1, then some point is a no segment. Now use this observation along with this to finish. So, Ahan Pani, the point is you have to show that for some period works for all of them. So as we slide C from 0 to 1, why is it that some C makes all of these translations of the intervals miss an integer? Okay, the observation is
I got that, but just saying that move C from 0 to 1 uniformly doesn't prove that. That's literally what we just have to prove right now.
Yes. Yes, that is exactly right. Like you can't just say move C uniformly because that's sort of a circular reasoning. Can you repeat the observation? Yes. The observation is that if you have an interval 0 to 1 in a bunch of intervals whose sum is at most 1, the sum of lengths is at most 1, then there is some point in no segment. It's very similar to what we were doing above, but flipped around basically. Okay, so now the finish is very easy now. Do you all see it? So basically what you'll do is, say you have this interval an to bn, say it's something like 0.4 to 1.2. You take a sort of projection, quote unquote projection, into the interval 0 to 1. So what it becomes is, it becomes 0 comma 0. No. It becomes 0.4 comma 1 and 0 comma 0.2. The projection. Do you all see why this is the case? Because intuitively what we're doing is, we have the number line, we have 1 here, 0 here, 2 here, and this interval, we're just projecting it onto the thing by translating each part of it into 0, 1. And now we have many of these projections into the interval 0, 1, whose sum of lengths we know is at most 1. Why is that? Because of this condition that we have from the very beginning. And now do you all see the finish? Yes, you could think of it as mod z. That's a better word to use. Or mod 1, actually.
But if an interval ai comma bi already contains an integer, then how can adding an integer c stop that?
T is not an integer, it's an arbitrary real
The
number.
real number.
So do you all see how to finish from here? It's essentially just the observation.
Since the sum is greater than or equal to n, we just have at least one point which passes through all of them, and then we're done. Since we had
In
that
fact, the exact
sum
opposite of what you
only.
said. The sum is less than 1, so there's some point in none of the intervals. Not one point in each of them.
Yeah, my bad.
Yeah. As someone said in the chat also. So some of the things is at most 1. We have that value of c and then we can translate it. Is this clear to everyone? I could summarize the whole argument once more.
You can summarize the last part. Just projected the legs into the unit.
Okay, so I'll redefine what I mean by projection. Basically, if you have some intervals, say 1.5 to 2.4, and we have it on the number line, and this interval is somewhere here, we do something like a modulo 1. So we take this part of the interval and we bring it over here into 0 to, comma 1. And then we take this part and bring it over here. Okay. And now basically we break each interval into maybe 1 or 2 intervals. and we are basically projecting it from 0 to 1. And now what we're doing is, when we have projected everything here, we know the sum of lengths is at most 1 because of the bi minus ai sum being at most 1 by the problem condition. Okay, so when we have all of these is in 0 to 1, there is something which is missed out, say C. Oh, wait, no, C is already used. Say some D. I claim that setting C is equal to minus D finishes. Why is that? Because the point is, for each interval A1, AI to BI, the claim is that AI minus D, comma BI minus D has no integers. And the reason being is because D doesn't belong to the projection. And if this did have an integer, then it would belong to the projection. Do you see why?
No, I don't get it. Can you repeat the projection part again? Are we splitting it into two parts and then putting the
Okay, wait, let me.
part before an integer? Yeah.
Okay, so say this say we have this interval which is 1.4 and 2.3. Okay, 1.4 and 2.3. What does the integers, the real numbers between 0 and 1, such that 1.4 plus c and 2.3 plus c have no integers between them? What does this intervals of c looks like?
negative 0.4 to negative 0.3, and here it's the what do you call
C
it,
is
the round
between 0
bracket,
and 1.
and you can just add a negative one then. So negative 1.4 square bracket, and at the end negative 1.3 and round bracket.
Wait, I didn't get what you're saying. Like, I'm saying between 0 and 1. Like, you're not telling me a real number between 0 and 1. Okay, so the set of real numbers would look something like this. It would look somewhere between 0.6 and 0.7. Do you all see why? Say you have 0.67, definitely not planned. You have this interval becomes 2.07 and 2.97. Wait, no, I think I'm messing up the explanation a bit. Wait, let me just think for a second. Okay, let me just copy paste the explanation in the source I have. I think that would make it much easier. So this is the proof that I have. So the condition is equivalent to this no integer to be found in the intervals between ai plus c and bi plus c, which was the first thing I did, i.e. the translates of ai bi. Moreover, the sum of the lengths of these intervals is at most 1. Thus, we are asked to show that the union S of a finite set of non-degenerate intervals of total length less than 1 may be translated so that it becomes disjoint of the integers. Is this clear? This is essentially what the first pass first. Akshar,
How are you translating it? That's what I'm asking. And I don't get it.
do you get what we've done every? Okay, wait. Have you gotten AI plus C and BI plus C must have no integers?
Yeah, that's fine.
So you've gotten what this is trying to say. Now we'll come to the proof on why there exists such a real C. But you've gotten all of this now.
Yeah, that's fine. This is fine.
So for all k belonging to Z, consider the sets Sk of S intersection k comma k plus 1. We know S is the set of intervals we have. Okay. And what we do is we translate them Sk minus k into 0 comma 1. So essentially what we do is say our interval is 3.4 to 4.5. We intersect this with 3 comma 4 and 4 comma 5. This gives us two intervals. One is 3 comma 3.4 and 4 comma 4.5. We translate this into 0 comma 1. So that gives us 0 comma 0.4 and 0 comma 0.5. Is this clear?
Yeah, instead of let's say if AI and BI did not have an integer between them.
Like it makes intuitive sense now. Like I don't think this writer was properly done though. But did you understand what's going on basically?
Yeah, yeah, yeah. How does the translation work if AI and BI don't have an integer between them?
Okay, then it's even simpler now. Like if it's 3.4 to 3.7, then it just becomes 0.4 to 0.7. Okay, actually ignore this explanation the book has. Just consider the explanation I was giving before. Do you see why this works?
Okay, I see how the translation works, but why does it give us a value of C? Why does C equal to minus D work? I don't get it.
Okay, so say we have a translate which is 0.5 to 1 and 0 to 0.2. Okay. And the original thing was something like 4.5 to 5.2. And we have some value in between which isn't in our interval. So say 0.4. Okay. Now what I was saying is minus 0.4 works. And that is because when we translate this interval by minus 0.4, we get 4.1, comma 4.8. And that has no integer. And um that is the general thing what's going on.
Okay, yeah, it makes sense. Yeah, got it.
Also, this book I'm not allowed to share with y'all because it was given by a course. It's the course notes from a certain course I've done. And it's not allowed to be shared publicly. Okay, it's 5:30. Class should end. Do you all want to do just one last problem or should I end it here? Okay, I'll do one more. Um, is everyone fine with me doing one more or do you all have to go for something?
Fine.
I'll share the problem that motivated me to do this class in the first place. A problem that I found very, very cool. Um, I have stopped using the frame since it has gotten a bit messy. You know what? This problem will take some time. It'll take maybe half an hour to 45 more minutes, and I have to leave now. We could do a simple problem, but I don't think we have time for this problem now. Okay, I'll share a bunch of more nice problems in the P set. I feel like I didn't get to cover the really nice problems, which is a bit sad. Yeah, that's about it for the class. Yes, I'm gonna leave these as homework. I'll send you the problems home for the P set. I have like 15, 20 of them. I think you have access. Okay, so I'll end the meeting now. Can you name a book for combi? Nashir Mathur's book is a very good book for beginners. After you have done it, then you should go to Pranav Sriram's book. You're in India, right? Um, in India, Nashir Mathur's book is available. Then there's Pranav Sriram. It's available or it's freely available online. I could send a link on the OMC server if you can't find it. I feel like the best way to do it is just do problems. I think there are a bunch of nice handouts online also. And yeah, those two books are good for starters. Please share PDF. Rashil Mathur's PDF is not available online, and I hope it never will be. Um, Pranav Sriram's thing is available for everyone. I could send it to you. Let me just find it. Okay, there's an. Wait, let me just send it now. Actually. Okay, so Evan Chen on his website has a bunch of book recommendations. So you could go there. In fact, recently the Rashil Mathur's book has been mentioned on it too, which is very nice. Since his book was pretty recent. Actually, no, not pretty recent. This is the Pranav Sriram book. And in general, like Evan Chan's recommendations website has lots of stuff. So let me just send that. Oh yeah, I'm clowning on the spelling of yeah, you sent it. Thanks. No, Pranav Sriram is not for beginners. It's in fact quite unbeginner friendly. If you're a beginner, then doing the Sheel Mathur's book and another one Evan Chen mentioned in his website would be better. Yeah, I'll send you the link. This paper, so you have to access the view PDF. It's a, I think it should be a good introduction to Combi. So that's it for the class. Thank you. I enjoyed it too a lot. Okay, yes, this Archive paper is a very good Combi book. I can see from the table of contents. Thanks for joining, people. Bye. Can I end the meeting or will you? Oh, I can't end the meeting.